Hi everyone. In the second half of the lecture 7, the small signal analysis is introduced. Although the discussion is based on a diode, the small signal analysis is not restricted to the diode. In the Taylor series expansion, we wanted to represent a function near a point x0. A deviation of x from x0 is delta x. Here, delta x is assumed to be small enough. Then, the function is expressed by summing two terms, the function value at x0 and a linear term with respect to delta x. The first derivative of f evaluated at x0 is the coefficient for the delta x term. By using the Taylor series expansion, a nonlinear function is linearly approximated near x0. Let's consider an exponential IV curve of a diode. In this case, the diode voltage is an input variable and the diode current is an output variable. When we apply a DC voltage of 0.6 volt and a zero point 0.3 volt AC voltage, the output waveform is shown in the right figure. Is it sinusoidal? No. Due to severe nonlinearity, the waveform is highly distorted. Now, we apply a DC voltage of 0.6 volt and an AC voltage with an amplitude of 1 millivolt. Again, the output waveform is shown in the right figure. What is your feeling about the right figure? Is it still heavily distorted from the sinusoidal waveform? Compared with the similar figure in the previous slide, you can immediately notice that the distortion is not that severe. The same diode, the same DC voltage, underlying nonlinearity is the same, but only a sufficiently large AC voltage can detect the nonlinearity. I have important questions. When you know the solution for an amplitude of 0.3 volt, can you estimate the solution for 0.6 volt? Or, when you know the solution for an amplitude of 1 millivolt, can you estimate the solution for 2 millivolt? The answer for the first question is no. But for the second one, it is yes. It is because a linear relation between the AC input and the AC output is valid for a small amplitude. Consider a general case where we have a DC input voltage and an AC input voltage. When we have a nonlinear IV curve, the output current should be newly calculated whenever the AC input voltage is scaled. Consider a small signal case. Here we have a DC input voltage and a small AC input voltage. A linear relation is found between the AC input voltage and the AC output current. When the AC input is scaled, the AC output is also scaled with the same factor. We don't have to calculate it again. Since there is a linear relation between the AC voltage and the AC current, a small signal resistance is enough to represent their relation. This small signal resistance, R sub D, depends on the diode current. When the diode current is large, the small signal resistance is small. Note that the small signal parameters are determined only by the DC parameters. When a small AC voltage is applied to a diode, due to its linearity, the AC current response has the same waveform. No frequency conversion occurs in this case. In the last slide of part 2, an example from Rajavi's textbook is shown. When the DC current is 1 milliampere, the small signal resistance is about 26 ohm. When 1 millivolt is further applied, the additional current would be 38.7 microampere. When the DC current is reduced by a factor of 1000, the small signal resistance is increased 1000 times. In the next video, we will quickly move to the MOSFET, the main theme of our lecture. Thank you.